that reason. So those nuclides which are having binding energy per nucleon more, and they are said to be stable. And those nuclei which are having less binding energy per nucleon, they are less stable is what? Like this, what happened? We make a firm conclusion. Okay, now let me draw the curve. One curve is there. Just a theoretical idea, nothing is there. How to calculate binding energy? Already we have just discussed in a rough way. There's a mass number A. This is binding energy. Nucleon, this will be in terms of mega electron also. In books, we just call like this, binding energy per nucleon. So if you look at the maximum it is, so in terms of 2, let this be 2, 4, 6, and 8. Iron it is 8.5, no? So this will be 50, yeah, let me take this as 50, 100, 150, 200, 250. The curve, almost all books, the same method is giving. $56 iron will come here, no? Yeah, this will be iron. Next nitrogen, how much will be? 39. One more color. A 10 mega electron volt. No, first we'll show the iron. Iron will be around, it is 8.51. 56 it will be. Nitrogen also will be more than 8. Below it will be 1. 1 will be deuterium. Tritium 3 it will be. You need to remember helium, lithium, okay, the curve will join it. Arsenic will be 70, no? Around, yeah, 70. How much, what is the lead PB, no? Lead symbol, okay, not needed. Arsenic, ZR. Uranium, so we'll go for bismuth. Bismuth, anybody number? 209, huh? Oh, yeah. 209. Uranium 238. 209 will come here. Uranium will be 238. And the stability curve, this is the iron, Fe. So this is the bismuth. (209) and 83. Uranium 238. 92. This is deuterium, tritium, helium, then lithium, oxygen, nitrogen. I'm just showing few. So if you refer book, they are shown plenty of that one. So to just put like every nucleus, though n greater than z, you can look at that. They give you number of protons and number of neutrons. Though they are more open, it is unstable. It is still unstable. And if you look at the middle weight, so what you do classify this into two parts. This is called like a lighter weight, heavier nuclei. These are called as the middle weight. Why middle weight are more stable? Because they're having more binding energy per nucleon. So those particular nuclides which are having more binding energy per nucleon, they are more stable. So some undate. So let this be. What is the name of this? Sridhar. You look at this middle weight. 75, 33. Look at this one. So these are middle weight, no? They are stable. And lighter nuclei. You look at this. They're unstable. They're unstable. Then what about heavier nuclei? Though n greater than that, they're unstable. The reason for that, binding energy per nucleon. Why the middle weight only are more stable? So if you look at that particular nucleon, 56 nucleons, no? So I think you take marble. Then you take favicol, all of you know favicol. You take favstick will be very cautious. You take favicol. Then you just place marbles, like connect it. So what happened to a given marble? So in the diagram I'm showing around 6, but what happened practically? What happened? I think around some 14 or 16 marbles. What happened? A given one marble can come in contact with those things, those many marbles. If you take the marbles, what happened if you start connecting them? No? So like this here also marbles will be there. So and next again you put marbles like this. You keep on join them. So those marbles, those around, if you take the marbles which are around the range from say like a 50 to almost you can say around 100. Then what happen? Given this marble will have more interaction with all, because what happen? The surface area will not decrease much. And as you increase the atomic number, the number of nucleons increases, the surface area increases. As surface area increases, what happens? Those molecules or those nucleons which are at surface, what happens? They will have less interaction. No, sir, here also. But if you look at this and you draw some 100 or 200 nucleons. If you draw 50 nucleons, the distance between these nucleons, what happens? Will be still around less than 2 femtometer. But when you draw 100 nucleons like this, and the distance between these nucleons you take it, it'll be more than, so what happen? Around 2.5 or around 4 or 7 femtometer it will come. So they show that they are weakly bounded. Though they lie on the surface diametrically opposite, but the distance between these two, how much it is? Around less than 2.5. So they're interacting strongly. But as you increase the number of nucleons, so suppose at 200 nucleons you draw it. When you take these two nucleons, the distance between them what happen will become more than 2.5. It will come around 5 or 7 or 6, that one. Then whatever nuclear force will become very weak. And by chance, if they become proton, the electrostatic force will dominate here. And they are unstable. They call it a surface effect here. So shall we put like this? For the middleweight nucleons, what happen? The nucleons are where the given nucleon will interact with more number of nucleons. And hence they are tightly bound. The binding energy per nucleon will be more. Lighter weight. What is the problem with the lighter weight? Lighter weight, suppose you take 3. What is the interaction? It's only 3, no? You come for this. This given nucleon will interact with more number, no? Here what happens? Though there are only 3, less interaction. Sir, what about here? Here also more nucleons, more interaction, but you look at this outer nucleon. I'm not talking about the inside nucleons, somewhere here. These nucleons what happen will have less interaction. Don't talk only the one which is middle. One which is middle, okay, no, not a problem. The one which are on the surface is a problem. So only 3 interactions, very weak interaction. So therefore what will happen here? That they are not stable. Middle weight, a given nucleon, either you take this nucleon or this nucleon, will have very more interactions. Even this nucleon will interact with this also. Of course, it will be less than this nucleon. So therefore here what will happen? You can say the interaction between nucleons is more and they're very tightly bound. So therefore they're stable. What about every nucleon? This nucleon, no problem. Is a tightly bound. What about those on surface? They're not tightly bound. So like this, as the number of nucleons increases, the surface area increases, the surface effect, what it will do? These nucleons are not tightly bound. So because of that, stability will not come into picture. So this effect we show how to hereafter define stability. Just take the binding energy per nucleon. When I plot the binding energy per nucleon curve with mass number, then what happened? I got a curve. Then those which are stable, what happened? They're having more binding energy per nucleon. So therefore, hereafter to define the stability, I'll prefer the binding energy per nucleon because that will help us a lot than any other quantity. So therefore, this has made now universal. A good example now, you can see that one. Deuterium, tritium. It's helium is stable, but lithium again not stable. Tritium, deuterium, again bismuth, uranium. So these are not stable. So like this, what happen? We'll get a oral explanation like this. So to define stability, what happen? We prefer binding energy per nucleon because it is giving exact reason. So like this, what happened in SC Verma, that surface effect, everything that already I explained in the binding energy equation systematically there. So all this, what we put it to explain stability, what happened? We do prefer binding energy per nucleon because that will give exact reason. Okay, now one which are stable, it's of, let's not bother, no. So I'll think I'll shade it like this. We'll do one thing. Middleweight, these are so we'll give name. These are heavier nuclei. Middleweight nuclei. These are lighter nuclei. Okay, let's get into. So I am bothered about now what? That heavier nuclei, which is stable. So to attain stability, what it will do? Let's come back to this equation. Now look at this particular thing. You look at this particular dot. It is unstable, no? Because it doesn't lies in this stability region. Yellow color shaded region indicates stability. Now look at this particular. It is what happened. It's unstable. Somehow what happen if it can decrease some neutrons. say if it decreases 2 neutrons, 2 protons, it can attain stable, no? And look at this particular thing, nearby stability curve. So to attain stability, what it can do, if it can decrease 1 proton, and look at this, if it can decrease 1 neutron, it will enter stability. So like that, what happens? Those nuclei which are there nearby stability curve, if they can decrease few protons or neutrons, they can attain stability. And which are far away, what they do? Suppose they are far away, they will decrease neutrons, protons, like that. Or they sometimes they decrease both neutrons, protons. Sometimes they decrease only neutrons, only protons. Like that, what happens? They keep on decrease their nucleons to attain the stability. So what this heavier nuclei will they do? To attain stability, what they do? They'll decrease their number of nucleons. How do they can decrease here? As a phenomena will occur where it will decrease nucleons. So if it decrease means, for that what it should do? To attain stability, what happen? The nucleus what happen starts emitting nucleons. It starts giving out nucleons. This particular phenomena is called like a radioactivity, which we are going to study here. So those which are unstable, what they do? To attain stability, what will happen? They will decrease their number of nucleons. So the nucleus starts emitting nucleons. And that particular phenomena is what called a radioactivity. That particular radioactivity. So what are the possible types of particles that will be emitted? So next we'll go for nuclear reactions. I'll have water. When the atom will be stable, if the nuclear force and electrostatic force, if the somehow they act in such a way that they'll get balanced, then they'll be stable. That's what happens in case of middleweight. What happens to heavier nuclear? The electrostatic force will dominate on the long range force will dominate on the nuclear force. Same thing here also, like the electrostatic force is able to dominate the nuclear force. Because of that, they're unstable. Where the nuclear force and the electrostatic repulsive force, if they're able to balance each other, it will be stable. So those particular nuclei where the electrostatic force dominates over nuclear force, then what happens? They'll become unstable. And to attain the stability, what that particular nuclei do, then they'll better try to decrease the number of nucleons. They decrease the number of nucleons. So because of that, particular what happen, as it decrease the number of nucleons, we'll say decay. It will just decay on its own. It will decrease the nucleons. No need of any external agent. The nucleus